All right, let's just get right into it. We've all been there, right? You're using an app, you try to scroll, and it's just stuck. Nothing happens. It freezes, it stutters, and it drives you absolutely nuts. Now, for developers, this is way more than just frustrating. It's a critical failure. It's the kind of thing that makes users just give up and uninstall. So today, we're going to solve one of the most common crimes in mobile development, the unresponsive application.
That's exactly right. We are treating this whole thing like a crime scene. The victim? User experience. And the evidence is just everywhere. You've got that sluggish scrolling, taps that take forever to register, and of course that one dreaded message that tells us our app has just given up. Our job is to follow the clues, finger the culprits, and basically bring our app's performance back from the dead.
So, let's take a closer look at this crime scene. What are we seeing? Well, the main symptoms are an app that just feels laggy, you know? Animations stutter, scrolling is choppy instead of smooth, it just feels broken. And all of this leads to that final, damning piece of evidence that Android itself throws in the user's face.
Ah, the ANR, the absolute terror of every single Android developer. This little dialog box is the operating system basically stepping in and telling the user, hey, listen, this app has completely stopped listening to you. It pops up when the app's main thread, you can think of it as its central nervous system, is blocked for 5 seconds or more. And for 5 seconds, it's been totally unable to process anything you're doing. This right here, this is our smoking gun.
Now, check this out. To really understand the pressure we're under, you have to look at this number. On a modern 120 Hz screen, a developer has just 8 milliseconds. Not seconds, milliseconds. That's all the time you get to do everything you need to do to draw a single frame. That is literally less time than it takes to blank. If any single thing you do takes longer than that, the user sees a stutter, what we developers call jank. The margin for error here is razor thin. It's crazy.
So, who's the main culprit in all these performance crimes? Well, in pretty much every single case, the investigation leads us straight to one prime suspect, the UI thread. It's also known as the main thread, and yeah, this is where the trouble almost always starts.
You know, think of it like this. Your phone's processor probably has, 8 cores? So that's like having an 8-person orchestra ready to play. But the UI thread is just one single worker. So if you make that one worker do all the heavy lifting, like processing data, making network calls, and trying to draw the screen, it's like telling only the violinist to play all the instrument parts. The other 7 musicians are just sitting there doing nothing, and the whole concert grinds to a halt. You're just wasting almost all of your device's power.
Of course, the UI thread rarely acts alone. It's usually getting bogged down by a whole lineup of accomplices. These are the operations that have no business running there in the first place. So let's bring them in for questioning.
And here they are, the usual suspects. First up, you've got expensive UI work. Things like FireMonkey-styled components can be surprisingly heavy, or maybe you're drawing thousands of shapes on a T-canvas. Then you have the silent killers, inefficient memory management that creates bottlenecks, long data processing tasks, and oh yeah, the classic mistake, making a network request and forcing the entire app to just sit there and wait for the server to answer. Any one of these can freeze your app solid.
And look, this isn't just some theory. Let's look at the hard evidence. This data right here compares performance on the exact same hardware, but running Android 11 versus Android 14. The number of janky frames more than doubled. The count of a slow UI thread nearly tripled. The really crucial thing to get here is that as Android evolves, performance is actually getting worse for apps that aren't optimized. The need to solve this crime is more urgent than ever before.
All right, enough about the problem. Let's start talking about the solution. To crack this case, we need the right detectives on our side. And in the Delphi world, our 2 best investigators for this job are T-Thread and T-Task. These are the tools that let us finally move all that heavy work off the poor, overloaded UI thread.
And this just shows you the difference they make, plain and simple. On the left, a big task kicks off right on the UI thread, and bam, the app is a block of ice. The user is stuck, they're tapping the screen like crazy, and that ANR risk is through the roof. But on the right, that exact same task is offloaded to a background thread. Look at that. The UI stays perfectly responsive, the user can keep scrolling and tapping while all the heavy lifting happens silently in the background. This is the secret to a well-behaved app.
Now, the good news is that modern Delphi makes creating background threads super easy with something called anonymous threads. You can literally define and run a whole task in just a few lines of code. But it comes with this classic, almost funny mistake that I swear even senior developers make. You write all the beautiful code to create the thread, and then you forget to actually call .start to make it run. The code looks perfect, but absolutely nothing happened.
So now that we've got our detectives, thread and t-task, it is time to close this case. We need to interrogate them a little bit, figure out exactly how to use them the right way, and then deliver a final verdict on the best practices for building a truly responsive, high-performance application.
Okay, so once your background thread finishes its work, it has to report back to the UI thread to update the screen, right? There's a golden rule here. Only the UI thread is allowed to touch UI components. Synchronize and queue are the two ways to do this safely. But here's the huge difference. Synchronize is like making a phone call. It forces the background worker to stop everything and wait on hold until the UI thread is done. Queue, on the other hand, is like sending a text message. It just fires off the message and moves on immediately. It doesn't wait around. Using queue basically decouples the two threads, and that leads to way better performance.
So which detective do you call? Well, think of it this way. Task and the parallel programming library, that's your modern multi-lane superhighway. You should be using this like 95% of the time. It's built for getting things done safely and quickly. T-thread, that's more like a precision scalpel. You only break that out for that special 5% of cases where you need absolute surgical, fine-grained control over every little detail. For pretty much everything else, T-task is the right tool for the job.
So, the verdict is in. Here it is, your action plan to eliminate ANRs for good and make your app feel fast and fluid. Step 1. Audit your code. Hunt down every single use of that blocking tthread.synchronize call. Step 2. Replace them with a non-blocking tthread.queue wherever you possibly can. Step 3. Find any heavy lifting that's still happening on the main thread and get it moved to the background. And finally, step 4. For any new background work you write, just make the parallel programming library and t-task your default choice from now on.
You know, following this plan will solve the huge majority of performance issues and make your cross-platform app feel truly native. But that leads to the final, much bigger question that we'll leave you with. At what point does all this effort, all this complexity of optimizing a cross-platform solution, at what point does that outweigh the benefits? And does it just make more sense to build natively from the start? That's a huge architectural decision every single development team has to face.